have just seen a simple example of evaluating a term in the innermost leftmost strategy. Let's look at the same term again in outermost evaluation. So we always evaluate the outermost term. In this case, this is this square here. We evaluate this square and get square 2 times square 2. We cannot evaluate the multiply symbol because we need two numbers for that and not expressions. So we have to continue evaluating this expression here. And it yields square 2 times square 2 times square of 2. We now can again evaluate only one of the square terms here. We pick the outermost, and this yields 2 times 2 times square of 2 times square of 2. Again, we pick the outermost term, which is 2 of 2, reducing to 4, multiplied by square 2, multiplied by square of 2. We evaluate the next square of 2, which is 2 times 2 times square of 2, finally yielding 4 times 4 in the next step, which we can now evaluate here, getting 16 times square of 2, and there are a couple of other steps after which we finally end up with 16 times 16, which is 256. Now, these are 14 steps in total compared to the 6 steps before. Have a quick look at it. Certainly, innermost evaluation must be better if it takes less steps to compute. That is, in this case, definitely true, but there is another side of the coin. A function that picks the first element from the list. Let's consider that function. So it's a simple function, we call it first. It is called on a pair of integers and returns an integer. The definition is first of the pair mn is m. Can we combine this with a function that does not terminate? For instance, a function called infinite that takes an integer and returns an integer, and the definition of infinite n is 1 plus infinite n. You can try to evaluate this function, it will never terminate. Now let's look at the results for outermost and innermost evaluation for the following expression. First of the pair of 42 and infinite 1. Try to evaluate this expression in innermost and in outermost evaluation. What is your result? If you compare this to the lambda term lambda x 42 applied to lambda x xx applied to lambda x xx, then I hope you will see a similarity to these two terms if you have evaluated them both. As you may have seen now, termination of outermost evaluation can happen even if innermost evaluation does not terminate. So if an expression E has a normal form, then this normal form can always be reached if you do outermost evaluation. Intuitively, this means the following. Outermost evaluation terminates most often. The question is, could there be more than one final result? i.e. two possible ways to terminate but give you different end results. And the answer to this question, or the property that this question is about, is called confluence. Depending on the order of evaluation, could there be more than one final result? That means, can computation in the lambda calculus be non-deterministic? Can I reach different results? And the result of this question, the answer to this question is that no, the lambda calculus is deterministic. The confluence property essentially says in its definition, let E, F, and G be three lambda expressions such that we can reduce the lambda expression E to both F and G. Then there exists another expression, lambda expression H, such that both F and G reduce to H. This definition is less complicated than it sounds at first. It just means that if you happen to be able to reach two different intermediate results of a lambda expression, then you can always continue the evaluation and reach a common lambda expression. Confluence therefore means if I reach two different expressions from following different evaluation strategies, I can always find a common successor expression. That means intuitively that every terminating expression can eventually be reduced to the same normal form, no matter the strategy. There are consequences of confluence which are really important. Any evaluation strategy, if it reaches the same result, if it is existent. That means if the term has a result at all, and that it does terminate. Outermost evaluation can deal with possibly infinite computation. This is something really interesting. It is also referred to as lazy evaluation. Why is it called lazy? Because it only evaluates expressions that are needed to progress the computation. Lazy sort of is a form of outermost evaluation. It's not exactly the same. Try to think about it for a moment and see if you can come up with differences. So, confluence is a property of the lambda calculus in the first place, but it extends to Haskell and all other functional programming languages. Because essentially, Haskell is the lambda calculus. You can recall lambda expressions and anonymous functions in Haskell, and you see that they are virtually the same. All other function definitions that you have above the lambda calculus in Haskell are just syntactic sugar in a sense. They just make the program easier to read. All functions could be defined with lambda expressions. Of course, this would look ugly, I agree with you here, and it would be very tedious to code, like coding assembly language. But it has the same functionality. You could write any possible program. The consequences are that Haskell programs have the confluence property, which is nice because it means that you can use outermost reduction and you can deal with possibly infinite computation. To give you an example of lazy evaluation, in Haskell you can have infinitely long lists in a terminating program. For instance, let's define a function infinite ones that takes no argument and returns a list of integers. The definition of infinite ones is 1 appended, and we append to 1 infinite ones again. This yields 1, 1, 1 forever, or till your computer runs out of memory. But you can still use such a list, it's still useful. Let's define a function take that gets two arguments, an integer, a list of values of type A, and returns a list of values of type A. The definition is done in 3 lines. Take of n and an empty list is always the empty list. Take of 0 and a non-empty list xs is also the empty list. And take of n and x and the rest list xs is x appended to take n minus 1 xs. The program take 5 infinite ones terminates. Why is that the case? What is the result? Feel free to copy this function into an integer and try to evaluate it with the Haskell interactive compiler. Are there problems? Is this all good and fine now? Can we always get a normal form for anything? Do we have Confluence and can hence do lazy evaluation in functional programming? Do we always get a unique result? Can it be that easy? Unfortunately, it cannot. But because if it was, no one would ever have to worry about concurrency bugs, race conditions, etc. And this is where we enter side effects. So Haskell has lazy evaluation. That means you only evaluate what you need to progress the computation. But what happens if it does not matter what we do next? So in Haskell you may have two terms, 2 plus 3, and the term 2, 3 plus 4, and your function is term 1 times term 2. Which term should be evaluated first? In Haskell you have no guarantee which is evaluated first. You have no explicit control flow which says first this, then this. In contrast, C++ does have explicit control flow. In C++, if you write int term is 2 plus 3 and int term 2 is 3 plus 4, and finally compute the result f term 1 times term 2, what happens in C++? Essentially, term 1 is evaluated first, then term 2, and finally f. Again, we see the difference between imperative and declarative programming. Imperative programming, as I mentioned at the start of the course, means here is a list of commands, do exactly like this. And declarative programming means the result should be the multiplication of these two terms, but I don't care how you do it. In particular, I don't care in which order you calculate the terms. This gets problematic when we are dealing with so-called impure functions. So let's distinguish pure and impure functions. A function is pure if it always returns the same result for the same input value. No hidden information influences the outcome. Also, the function does nothing else besides computing the result. Examples for this are mathematical functions such as factorial, Fibonacci, sine, cosine, etc. This seems at first glance a bit trivial. Of course, a function always returns the same result for the same input values. Actually, it doesn't. And this is where we enter impure functions. An impure function's result can depend on additional external and hidden factors. That means that the function can also do side effects besides returning a result. For example, I/O is an impure function because it prints prints values to the screen. It reads input from input devices and may also return some result that is different every time depending on the input it has read. Also, direct memory manipulation is an impure function because it not only returns a value, but it also changes the state of the machine. Exceptions are a different example because a function may either return a value or an exception value depending on what the input value is. Also, any void function is an impure function. Why is that? You can pause the video for a moment and try to think about it. The answer to the question why is any void function an impure function is that a void function does not return any value at all. That means it has to do something else on the side, else it would just be an empty function. So informally, a pure function is like a drink vending machine. You have some input, say you put coins in the machine and you press a button which drink you want to drink. And you get as an output some drink which means equal output for equal input. I can do this as often as I like. I will always, for the same coins and the same button push, I will get the same drink, provided the stock does not run out. Informally, impure functions can be seen like an ATM. You have an input which is an ATM card, a pin, and a desired amount. As an output you get cash. But there are side effects happening. And how do they influence the output? What could possibly happen here? Again, try to think about it for a moment by pausing the video. Possible side effects that might happen would be as follows. First, I might not get any cash at all, which is essentially like an exception, because either my PIN could be wrong, or I could not have money on my account, which is why the ATM would deny giving me money. Also, there is a very important side effect that is not reflected in the cash that I get, because the money on my account is actually reduced. This is something I do not see on the result, i.e. the money bills that I get out of the ATM. So side effects such as the state of my account influence the output. The problem with this is that side effects suddenly make the order of evaluation important. But Haskell has no fixed order of evaluation, which means that there are no simple side effect functions in Haskell. So imagine we had actually some Haskell function that is called read from input and returns an integer. We could then have a function called evil minus that also returns an integer, and the definition of evil minus would just be read from input minus read from input. What would be the problem with this? The problem would be that we have no guarantee which of the two read from input function calls is evaluated first. So if I enter two different numbers with my keyboard and feed it to the evil minus function, we do not know which of the numbers would end up in the first function call and which would end up in the later, giving you two different results. Compare this to imperative code. We have a function called minus. It has you declare two variables x and y and read from the input two numbers and then return the subtraction of y from x. Why is this fine? It is fine because we have a guarantee that reading the input into x always happens before reading the input into y, which is not a guarantee that you have in Haskell. As a summary, if you have side effects like I/O in a program, Confluence no longer holds. You no longer have unique results. The thing is, why does this work in the lambda calculus? It works because the lambda calculus does not have I/O. But in a real programming language, we need I/O, we need networking, we need memory management, we need to access the state of the machine. How can this be done in Haskell, is the question. There is actually a solution in Haskell, not surprisingly, and that is that you can enable a fixed order of evaluation when needed. There are some special types in Haskell called monads, and whenever you do something with a monad type, the order of evaluation is fixed. But the rest of the program that is out of this monad part of the code is still evaluated lazily. This is a strong simplification, and you can do a lot more with monad types, but unfortunately this would be well out of the scope of this lecture. So for now, let's stick with this simplified intuitive definition of monads. So let's say we have some function IO minus, which does not return an int, but some type IO int. That means an integer that was created by doing IO. And we have the IO minus defines as do x goes to read int, y goes to read int, and you return x plus y. So if we write it like this, you see that the syntax is different. Then x is evaluated or read first, and we get unique results again. Now, why is it good to not have side effects in the first place, or rather strongly restrict them? One main point is that parallelism and concurrency gets easier to do. In multi-threaded programs, you have no guaranteed order of evaluation, which already sounds like Haskell, and by restricting side effects, you can avoid race conditions. Think of what John Carmack initially said when I presented the quote to you. Programming and by restricting side effects always has benefits. So the summary of side effects are that they are everywhere in practical programming. Of course, you access your hard drive all the time, you print stuff to the screen all the time, and you do networking. The important thing is that you should be aware of them. Try to keep your program side effect free if possible, and restrict the side effects to certain parts of your code. If you manage to pull that off and encapsulate the side effects in certain I/O parts and have a pure computation part of programming of your code, then you will have less bugs in your applications. I can guarantee you that. And functional programming is a great help with this because it really forces you to restrict side effects.